So let's get started, and welcome to the last colloquium of the quarter, of the year, at least of the calendar year. It's a great pleasure to have Matt Evans here from MIT to talk about Cosmic Explorer, right? You guys call the thing. That is the next generation interferometer gravitational wave observatory. Matt was an undergraduate at Harvard-Mudd. And then a graduate student at Caltech. He stayed on as a postdoc at Caltech and then also worked as a postdoc at Virgo, that is the European equivalent of LIGO. And then he's been, I don't know since when, but a professor at MIT. He has received a number of, he is a fellow, he is an APS fellow, and he received Breakthrough and Gruber Prize along with LIGO collaboration for the observation of gravitational waves, but most recently he also received the New Horizon Prize from, again, from the same establishment that has the Breakthrough Prizes, more specifically to him and a couple of colleagues at Caltech at MIT. And so he will be telling us about the next generation interferometer gravitational wave observatory. Thank you.
All right, so let me start by trying to get my technology operating here. Switch. Is the switch on? Yes, switch is on. Working? Yes, okay, good. This is a big room, so that's important that works. And next trick. Haha, okay, awesome. So I gave a colloquium here a year ago. And if you saw it and likely enough to be here today, raise your hand. Okay, that wasn't very satisfying. If you saw it but didn't like it enough to be here, raise your hand. Okay, that's a great ratio, right? Right? All right, so anyway, that was my icebreaker to get us started. So I'm not planning to spend, I should use this clever device I have. I'm not planning on spending most of my time talking about LIGO, but let me give a little bit of background. And anyone who hasn't, I feel like I've said this so many times that everyone has already heard it a lot of times. It's probably not true. So if I say something that makes you want to ask a question, please just feel free to raise your hand or shout out or whatever and ask your questions. I don't mind being interrupted, so do as you like. LIGO has been going along, doing its thing. Detecting gravitational waves now since 2015. And we started out in our first observing run of advanced LIGO, the current detector. And we ran for about a year, so 2015 to 2016, and we detected three sources. And they're binary black hole systems of various masses that are shown here with their code names and all of that. We shut down for a while, fixed the detector, and then turned it back on and ran for another year and collected another 8 sources. One of these was particularly interesting because it was not a binary black hole. Actually, all of them were interesting, and there are people who love each and every one of these sources because they're all still special, even though we're now at almost 100, maybe some of these are not special, but most sources have somebody who loves them for one reason or another. But here we have this one, which is starting with 2 neutron stars and ending up with, I don't know what that is, at 2.8 solar masses, probably a black hole. Okay, so that was momentous detection because it wasn't just LIGO, Virgo was involved, and it wasn't just LIGO and Virgo, it was a bunch of telescopes all over the Earth and out in space, pointed at this event, and were able to observe GW 170817. So that was our first binary neutron star detection. The first and best ever. Oddly enough, this was the first and arguably still one of the best binary black hole detections. So anyhow, that was the second observing run, 02, and then we shut down for a couple of years and came back on and ran 03, starting here. And in 03, instead of 8, we're at something like 80 events gathered up there. There were They were all possible combinations in the sense that we detected a bioneutron star, we detected a black hole neutron star. If you look at the ones that are filled in, like this guy is, those are the neutron stars, the ones that are black are not. So you have a black hole and a neutron star, probably, it's 2.1 solar masses. We have some things that it's unclear what that object is at the beginning, 2.6 solar masses, anyone? So anyhow, another black hole neutron star combination and so on. Unfortunately, none of these were localized well enough for them to be detected. One could argue that the black hole neutron star sources that we detected probably did not have an electromagnetic counterpart. The black hole can just eat the whole thing and you don't get any bang out of that. Anyhow, this is the catalog, if you want, of sources detected so far. So there's a lot of interesting things in each one of them. There'll be the biggest one is in there. There'll be the one with the highest spin. There'll be the one with the largest mass ratio. There'll be the one with the, and so on. So all of these things are interesting in their own right. Yes?
Why did you say the first one was the best one or the favorite?
This one?
Yeah.
It was close. So the signal to noise ratio was high. And it was so high that when we first detected it, I and I guess probably other people, but I suspect I was the first person to do this. I filtered the signal a little bit and just plotted the time series like you would on an oscilloscope. And you could obviously see the signal. So, I mean, it was huge in some sense. Most of the sources we have require at least some sophistication to see them above the noise. So yeah, and maybe just because it was first, it was also my favorite, but the signal noise ratio was quite high. And it has become a canonical source in terms of the masses. The 30-30 kind of combination is pretty common sort of thing. So it's one of the loudest and sort of a typical mass. That's why I like it.
What's the meaning of the blacker background in the lower 2.5 rows?
So O3 was separated into two parts, A and B. And that's the sort of slightly different coloration that's here. And as I'll say in a minute, O3b was meant to go a bit longer, but was interrupted by unfortunate global events in 2020. Basically everyone had to go home. So we stopped operating. So you might wonder why we had 3 and then 8 and then a whole bunch. Like, what is the huge change in the detector that caused this? And it's not really a huge change. I should use this thing. Come on. What happened here is that the sensitivity of the detector was improved, not by a huge amount, but since the rate at which we detect sources scales with essentially the volume of the space we're sensitive to, if we make a factor of 2 improvement in our sensitivity, we get something like a factor of 8, I'll just call it a factor of 10, change in the rate at which we detect sources. And as we went from the first observing run to the end of O3, so O3b, that's the kind of factor of 2 change in sensitivity, which caused this sort of factor of 10 difference in rate. So this plot is showing a cumulative collection of sources, the number of sources going along here is this black curve. And this is what we call the time volume product. So the gigaparsecs cubed takes the detection range, and then you say I make a sphere out of that, and gives me some volume in gigaparsecs, and I take the time I observe with that range, and I get some time volume product. And that's what actually determines the number of sources you expect, is the time volume product that you have. And so the accumulation of sources has been more or less according to expectations, which is shown by this blue line here through the middle. Not unusual. You can imagine that here at the end, or just before the end of O2, we were very disappointed, because we were sort of sitting here somewhere well below that line. And then right before we turned off, we got a whole bunch of events. Right? Sort of jumped back up. This felt sort of very weird. But then with time, it turns out that's just the way statistics are. So this is more or less the current state of affairs, is that we have a bunch of interesting detections, and we're, we've been working on the detectors now for a while. So what's coming next? The most immediate next is that LIGO will be turning on again soon. So in the spring, we plan to start operating again. we've been down since 2020. Some of that was down because of the pandemic. Some of that was down because we were working on upgrades. There are some momentous things happening which don't sound very exciting. So changing the optics out for optics that have fewer defects is an important part of this upgrade, and it's getting rid of a technical problem we had with some little absorbers on the mirrors. The maybe exciting part of this, at least exciting for us because we do this at MIT, is the squeezed light source. So in the previous observing run, we were operating with squeezed lights. It's a trick from quantum optics that lets us lower the noise. And just 2 weeks ago now, I was at the Hanford site, and we were able to get the new addition to our squeezed light source operational. I won't go into the technical details here because that's not what this talk is about. But this was 2015 at MIT when we had our prototype for this thing going. This is actually the pre-prototype or demonstrator. And this is November 18th, so 10 days ago, 11 days ago. We finally got a similar sort of cavity operational at Hanford, and there's another one in Louisiana which was operational on the same day, not entirely by chance. And there are a bunch of other smaller fixes. So the main piece of news there is that the LIGO detectors should be back up and running with somewhat better sensitivity again. It's not a factor of 2, it's a factor of 1.3 or something like that, better sensitivity. But then again, you cube that and it means the event rate goes up significantly. In terms of a timeline, this is sort of what that looks like. We started out in 01 back here and went through, sensitivity progressions that are all at the 20%-ish steps. This is where we're planning on starting. This is our COVID break and some upgrade time. And now we'll start running again over here for 04. Down for a little while again, do some more improvements to the optics. This is some work that's going on at the Coating Center for Coatings Research, CCR, here. We're working on new coatings for the LIGO optics, and we're hoping with those we'll be able to take another step in sensitivity. And then as we look farther to the future, we can say what's going to happen over on this end of the operation. And there we're thinking about what upgrades we can do after 05. So we call this the post-05 era out here. It seems far away, but if we're not making plans now, we won't actually be ready with hardware to install in 2029 sort of thing, 2030. That's not really that far away in terms of getting stuff ready to go. So you can think of this as we're just finishing installation here of stuff that we had planned a decade ago. This is stuff where we already know what we think we're going to do, so we have a good plan for this upgrade. And this is stuff that we're making plans for what to upgrade for the operation that will happen a decade from now. That would get us into the mid-2030s. And this will, at some point, you can probably see where I'm going, bring me to the main topic of this talk. So where do we go after that? So let's say that we've upgraded the LIGO detectors to the best we can imagine in that facility. We think we're really approaching the limit of the facility. And so we're thinking about, where do you go after that? And this has been going, this line of reasoning that I'm going to tell you about has been going since 2014, roughly, when we could kind of see the writing on the wall that we were going to saturate the current facilities, and we needed to be thinking about what would be the next big thing. And big in this case, I mean literally. So the reason why we think about building a new facility is because we'd like to scale it up. And I want to just motivate that briefly for people who haven't spent their lives thinking about how gravitational wave detectors work. So this cartoon hopefully will make the message clear. In a cartoon sense, our gravitational waves come from crash and burn. All right, I'll be right back. Or I will do a little dance for you if I have to get that message across. This is not because of we did not do a land acknowledgement, and I'll talk about that, but anyhow. It's not because of some recording gizmo, is it? No. Okay. So if this crash and burns again, then I will give up and not show you the video. Yep. Okay. So what that is two black holes going around each other, and this green stuff is coming out, and this green stuff are gravitational waves, and when the two black holes merge, the gravitational wave goes out across the universe. And eventually it arrives at Earth, and when that happens, you would see the Earth doing a little wiggly thing. The whole message there is essentially that there's an animation on this one too, and I'm wondering whether or not it's going to bomb, but anyhow. The whole message there is that the space-time ripple, which is a gravitational wave, which is a distortion of space-time, which sounds really complicated because it involves a lot of $10 words, in terms of an experiment, comes down to measuring some little displacements. And the trick is just to say how little are those displacements that you have to measure, and from an experimentalist point of view, you can then take all of GR and put that aside and say, I just need to measure these small displacements. How do I do that? And it turns out that the displacement you need to measure, here's another experiment in video technology. Let's see if we have any luck. The displacement you have to measure depends on the length of your interferometer. It's a strain, and that means it's a stretching like you would a rubber band. So the displacement is a fraction of displacement. A part in 10 to the minus 21 is what we're looking to measure. So the bigger my detector is, the larger the number of meters is that I have to measure. And that's what this is, a very simple equation is supposed to be telling you. So the delta L that you have, the displacement that you like to measure, is a product of the strain that's from your astrophysical source and the length of your gravitational wave detector. So if you take a, let's say, typical astrophysical strain, now we know this actually is typical, multiplied by the length of a LIGO detector of 4 kilometers, you get this 4 times 10 to the minus 18 meters number. And here we go. Yay. All right, so here's a hydrogen atom, and we're going to zoom into the proton. There's the proton, and we're zooming in, and now this box is 10 to the minus 17 meters. We're looking at the edge of the proton, and there's our displacement. Okay, so that's the scale of the displacement we're trying to measure for a 4-kilometer instrument to measure something like the events we typically detect. That's really tough in terms of precision measurement. And it turns out that despite a lot of people thinking for a long time, it's hard to make your sensitivity better by an order of magnitude in terms of displacement. So the reason why we think we should just make a bigger detector is because instead of trying to make our delta L noise lower, you can just make L bigger, and then the displacement you're measuring grows. So your signal is growing proportional to the length of your detector. If I make a detector 10 times bigger, I sort of naturally have 10 times better sensitivity. This little cartoon is Ray thinking about how to do this back in the 70s, right? Michelson, this is actually astounding. This was like with a lamp, right? A sodium lamp, in nanometers. But still, compared to this, you do much, much better. Okay, but now we have lasers. It's the 70s. Lasers are new and cool. Why not? Okay, so this brings us back to the first slide. And the basic idea here, is there a clock I should be looking at? Yeah. Yes. Oh, also over there. Okay. The basic idea here is to say, let's not try to be overly clever. Let's just make this thing bigger. Now that we know what the sources are that we're looking for, we know roughly the size of the strain we're after, we know what frequency bands might be interesting. Let's try to match the size of our detector to the signals that we're interested in detecting. And the highest frequency signals that we know of that we would like to detect are around a few kilohertz. And this is the post-merger signals from neutron stars. And so you wouldn't want to go much longer than about 40 kilometers, or else you start losing interesting stuff. You just lose that because your band is getting narrower, so you make the detector larger. That's really just light travel time down the detector and back. So that's a kind of natural scale, which happens to be 10 times current LIGO detectors. It also turns out that if you look at the curvature of the Earth and you ask, if I have a round Earth, this is a spherical cow approximation, but if I have a spherical Earth and I plop down 2 points that are 40 kilometers apart on that surface, and I draw a straight line between them, how far am I below the surface in the middle? And the answer is 30 meters, right? It's a long ways down, and that number grows with the square of the distance. So if you have a detector which is much shorter, then the depth you have to dig in the middle is not too bad. As it gets much longer than that, you have to start digging quite a lot in the middle. So if you go to 100 kilometers, right, you now have 120 meters worth of digging to do in the middle. Or you find a nicely bowl-shaped location. But it starts getting really tricky when you start making the thing much bigger than that. And it turns out that there's this additional factor that if you imagine, again, this is a physicist's approximation, but if you imagine that you need to move the dirt from the middle to the end because you're filling at the end and digging in the middle, right? You don't want to actually put them at grade on the ends and then dig a straight hole. You'll push the ends up a bit and dig a little less in the middle. But then you have a transport cost, which is growing linearly. And you actually end up with a length cubed in the cost of the facility. So 40 kilometers is a relatively happy length for a number of reasons. It seems like it's the longest you could practically build. It seems like if you were to build it longer, you'd be losing astrophysical signals, so probably you shouldn't go much longer than that. Our nominal concept for this thing is that we would have 2 observatories, much like LIGO. We would like to have, 2 that are identical would be fine. It seems like one 20 kilometer and one 40 kilometer facility would actually do good science. The shorter facility would be somewhat less sensitive at low frequencies, but it would have a little bit better sensitivity in the high frequency end, where you could have some neutron star, post-merger signals. So let's say the science optimization is relatively flat around that length for the second detector, but the cost is still growing quickly as you go from 20 to 40. So it seems appropriate to have a science per dollar maxima that's something like this configuration. So that's our reference concept for Cosmic Explorers. 2 observatories, 140 and 120 kilometers long. And that's the length of a single arm going out. So if you ask how much vacuum tube you need, it's 80 kilometers worth of tube. Which to someone in the oil industry actually sounds just fine. Like that's a week worth of the foundry. It just doesn't cost that much money. Okay, so there's a whole book, let's say, about Cosmic Explorer. This comes from some work that I did with a bunch of collaborators at 5 other institutions. And we put together this Horizon study, which develops the science case and talks about all kinds of good stuff for Cosmic Explorer. So if you want to dig into the details in any aspect of this, you can start with the Horizon study and see what's in there. I will just pick some highlights out of the Horizon study here and sort of speak to them as I'm going along. But you can find more depth on all of this stuff in there. So in putting this together, we picked sort of 3 areas for our science goals. We didn't want just a laundry list of all the possible things that you might be able to do with a gigantic gravitational wave detector. So we said, we'll have these 3 sort of areas. There's extreme gravity and fundamental physics, which has a number of different subtopics in there. Black holes, neutron stars throughout cosmic time. And again, you can think of some interesting subtopics. I'll talk a little bit more about each of these in the next set of slides. This is all about seeing neutron stars either run into other neutron stars or into black holes, so really exploring dense matter in a way that you can't easily on Earth. So you have some QCD that's in there, learning something about jets, could be interesting. Anyhow, all kinds of good stuff, but broken up into roughly these 3 categories. We didn't want to exclude the unknown, so it's in here as well. I don't think that we can reasonably ask the taxpayers to give us a few $billion and say, and we're going to detect something great, but we don't know what it is, right? So this can't be our primary thing, and at the same time, there would be a certain amount of hubris in saying we won't detect anything we haven't expected somehow. So we want that on there to acknowledge our ignorance of what's out there in its entirety. At the same time, we want the science to be something driven by sources that we're aware of. So this is all driven by compact binaries of one sort or another, either black holes, neutron stars, or combinations. I don't usually, in an astro type talk, put up sensitivity curves because not everybody has seen these things before and they take a little while to explain. I will try to explain this briefly and hopefully it will make enough sense that we can make use of this. So what this is showing is the way that instrumentalists usually talk about sensitivity of gravitational wave detectors. And it's in terms of the frequency on this axis, and this is the amplitude spectral density. So please ignore the crazy units of square root hertz, but that's what it is. Fundamentally, this is the noise in the output of your detector, and up like that is more noise, so you're winning if you go down. The band of interest is from 10 hertz to a few kilohertz. That's essentially identical to the audio band, especially for those of us who are a little older in the audience who can't hear anything out here. This is just exactly your audio band. This is great because it means that if you're diagnosing these detectors, you can actually just attach it to some headphones and listen to them. That was the way we used to commission detectors back in the old days, was just listen to the noise and you kind of got used to it. Your brain's a pretty good FFT operation going on in there, and you can figure out what's going on in your detector by listening to it. With nothing fancy in between. There's no artificial colors or anything. It's just directly like voltage into your headphones and away you go. So the gray curve here is showing the last run of advanced LIGO. The blue curve is showing where we're going in these next two upgrades. So the 04 and 05 upgrades should lead to this A+ curve right here. So kind of a factor of 2-ish, 2 to 3 better across the band. That's where we're heading in the next, out till 2028, something like this. The Voyager curve that's here represents, turns out there are a couple of technological choices that can get you to this, but it's representative of the best we could do in the current facilities, what we think is really the limit, when we've saturated the facilities, something like this. So a little bit better than A+, but you're clearly asymptoting as you go here. And then the pink curve here is the one I've been talking about, Cosmic Explorer. The green one, Einstein Telescope, is the European counterpart. It's a similar sort of setup. The detector design and technology is a little bit different, but the idea is very similar. So we would hope that these two detectors would be operating simultaneously. So from where we are now to Cosmic Explorer is a pretty huge leap. From where we expect to get is still pretty big. A lot of it is in the vertical direction, but there's also some opening up the lower frequencies here with Cosmic Explorer. And that comes from better suspensions, bigger suspensions, some sort of technical work on the isolation systems that's in there, and then addressing Newtonian noise concerns. And Brian will help us achieve all of this. Anyway, this part is really tough. Let me just put it that way. This is a very hard thing to do. So anyway, this is the sensitivity curves. Does anyone want to ask a question about those? Or does those sort of make sense? Yes.
The sharp peaks in the noise.
Oh yeah, people love these things. So the ET folks. So let's talk about the real ones first. So this is 60 hertz. That's 120 hertz, and that's 180 hertz. And this is the first one that's not a power main, and that's what we call the violin modes. So the mirror, which is our test mass, is suspended by some skinny little glass fibers, and they have, oscillations like a violin string does. And the fundamental oscillation is here, and then you can start getting harmonics, bop, 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 all the way up. So
It's the same like Cosmic Explorer and Einstein curves too?
yeah, so what's happening here is that is some suspension modes appearing in ET. This is some suspension mode in Cosmic Explorer. You should ignore those entirely because the detectors, let's put this, the suspension model that was used to produce that curve is not from an engineering design of a suspension. It's from someone like me who just took a LIGO suspension. It's like, what happens if you just make it twice as big, right? And you get some number for where your violin mode's going to end up, but it's really meaningless because you have to redesign the whole suspension. So these are not actually, I would say, meaningful things. Maybe the ET ones are more meaningful than the CE ones, but for Cosmic Explorer, I can say that's not really a meaningful little peak. So we try to make it kind of small so you don't see it too much. But yeah, that's what. So a lot of the features that you see here are, I guess I pointed the wrong one. So this is the 500 hertz one, should be the first violin mode there, and then you get the harmonics. But anyway, they're all things that we understand what they are, these features in the sensitivity. And some are just embarrassing power mains that we, like I guess everybody in the world, we can't get rid of. Fortunately, our European colleagues have a different power main, so it's not like everybody misses the same frequency. Other questions? Yeah.
Are you going to comment on what NEMO is?
Yeah, right. I was not going to comment on what NEMO is. So NEMO is a concept from our Australian colleagues. And the idea there, as you can kind of see from the curve, is to target higher frequencies, but really push the technology. So that's how they would hope to get to this sort of sensitivity level, but their aspiration would be to do that with a 4-kilometer detector. So the question that they were addressing with this design is if you took a current scale facility and focused entirely on high frequencies, what's the best you could do? And this is their guess. I think there's a lot of stuff in there that would be very hard to implement, but it's an interesting exercise that they went down that path, saying what could we do? And the reason for them to explore that is because eventually the global community would like to have one of these things in the southern hemisphere, and Australia would be a great place to build one. So they're looking at ways to start some observatory in Australia and build a community such that at some point down the road you could imagine building a Cosmic Explorer scale detector in Australia, which would be great scientifically.
Can you say a word or two about how you're going to push down the seismic noise floor?
Yeah, so some of this is redesigning the suspension in terms of let's make the stages longer, and that can let us move the vertical. So some of the cutoff here is actually coming from the vertical modes of the suspension. Since the Earth is not a plane, unless they're flat earthers here, I'm sorry, but if you have a spherical Earth and you put your suspensions on it, they're not parallel. So the vertical motion ends up being coupled to your laser beam that goes back and forth. So the vertical motion couples into your signal, and this turns out that longer detectors don't win in that way. But you can try to win by making the suspension stage longer and move the bounce mode, as we call it, down in frequency. So some of it's that. Some of it is just going with, basically just make the mirrors bigger, so a more massive system helps with the thermal noise in this region. Some of it is just the fact that we're 10 times longer, so you get a factor of 10 off the top in terms of the conversion from displacement noise into strain noise. Right, so here I'm plotting strain, so I've divided by the length. So I get a factor of 10 from that. I didn't talk about Brian's work on that. And he's looking at me like, why didn't you mention the isolators? Yes, and we're assuming truly awesome isolators with great sensors on them, and Brian will help us do that as well.
I was wondering, for all the considerations that have to do with the curvature of the Earth for Cosmic Explorer, are those already kind of taken into account for the 4-kilometer LIGO baselines, or are they kind of new, like some of the new features?
So it's in there, but the curvature of the Earth is so the vertical thermal noise of the current suspension shows up as part of our sensitivity curve. So it's there, but it's down. So it's at the same location in strain. If I make the detector longer, then the coupling grows with the length because the angle is growing, but I then divide by the length. So it turns out that in terms of strain, that the natural location of your vertical motion remains the same. So it's in there in the LIGO detectors, and it's determining some of the cutoff over here is the vertical modes of the suspension. All right, I'm going to move on, or I will not get to the end. So Good. If I take those curves and remember the colors, I hope I got them the same. I got rid of Nemo. I'm sorry to the Nemo folks. But they're not looking for horizon anyway. So this plot is showing the horizon distance, or the maximum distance to which we could detect a source with these various detectors. And it's as a function of the total source frame mass of the source. So I take two, let's say 30 solar mass black holes, and I say that has a total source frame mass of 60 solar masses over here somewhere. I assume they're in a circular orbit, and I say, what's the maximum distance to which I could detect that source? Put that in terms of redshift, and here's LIGO A+, sort of where we're going with the current set of upgrades. Voyager again here, the best we could do in the current facilities. And that's not bad, but for a lot of sources like by neutron stars, you're still very much local universe, and only for a sort of special set here do you get out past Z of 1 for your detections. If you go to next generation detectors like Cosmic Explorer or ET, you end up with the horizon for basically all of the masses you could expect is out past Z of 10. And the horizon for things that are in the sweet spot here, the total source frame mass between, let's say, 10 and 100, is out to Z of sort of crazy, where you don't expect anything. Well, I don't expect anything, but maybe some of you do. Okay, so that's the horizon plot. I'll show that again as we're going along. If I put that in a donut mode and throw down a source population or a couple of source populations, then this side is showing neutron stars, and this side is showing black holes, which are ironically white. And then the dashed curves here, again, the same set of detectors. So Cosmic Explorer is out here, this pink curve. So what that's intended to illustrate is that for binary neutron star systems, the sort of canonical mass, we expect most of them to live around the peak of star formation, Z of a few. And we expect to have a shot at detecting essentially everything that's out there in terms of binary neutron stars. CE is the best of all of these detectors for binary neutron star systems. ET is a little ways behind, but not much. Current detectors, right now we're here somewhere. This is our poster child source that was very close to home, but we don't really get into the bulk of the population with the current detectors. If you look at black holes, then right now we're sort of on the edge of getting into the peak of star formation at around Z of 1. And you can, say, what do you get with upgrades? Okay, now I have my horizon just past that peak. If I go to next generation detectors, then I'm out here into the region of I don't know what's out there.
Density of points is based on assuming star formation rate?
Yeah, so the density of points is assuming that the merger rate follows the star formation rate.
But these are supposed to be delayed relative to star formation, so I would think there should be more at the lower redshift.
Yeah, so I think the delay times, at least that were used in this model, the idea is the delay time is actually relatively short for the majority of our sources. So it's millions of years kinds of thing as opposed to billions of years kinds of thing. So I can go back to the horizon sort of plot and throw those populations on here. So the binary neutron stars are over here on that plot out to a redshift of 7, 8, something like that, depending on exactly the mass you pick. Again, I don't really expect any binary neutron stars out here, so that means we have a shot at pretty much everything. Our favorite and most common source are these binary black hole systems. Right now we're detecting the ones that are over here. But you could imagine that there are, there's a nice population of sources there from the first star, so population 3 stars. We would expect them to be heavier. I didn't draw these in any great precision, but somewhat heavier than our usual population, and at higher redshift. If you were detecting things out here, then this would be letting you address the heavy seeds versus light seeds question these are the intermediate mass black holes. So several hundred to thousands of solar masses. They're not the kinds of supermassive things we see in galaxies, but they could be the seeds of such things. So those guys would live over on this side. And I don't know if we have any fans of primordial black holes in the audience, but if we detect a merger at a Z of 20 or 30 or 40 or 50, then you might be hard pressed to explain it in any other way than something primordial. So that's this chunk. I don't know where they would be in mass space, but in terms of distance, it would be easy to distinguish them if they're at very high redshift. So if you're interested in looking into this kind of thing, there are papers published about this that do a more respectable job than what I did on that plot, of looking at different populations and how you could try to distinguish different populations depending on the rate as a function of redshift that you detect. Right? So I'd point you to this AppJ letters to go dig into that. I know that somebody asked me about this, so I thought I would throw it up there. And I hear a phone blipping, so I'm going to make sure the mine is silenced. It is, okay. Good. All right, so if you want an actual analysis of different populations that you can pick out using next generation detectors, you can find it here. So if I rotate on our science wheel to the green wedge, that was fundamental physics. And the idea is really that, of course, it's not just the horizon that matters. It's actually the SNR you have, the signal-to-noise ratio you have on the signals that you detect. And if you want to do precision measurements of gravity, precision tests of general relativity, I think the sources that you imagine are things like our first binary black hole. But that kind of source in Cosmic Explorer goes from an SNR of 30 to an SNR of 1,000 in Cosmic Explorer. So you get some very high signal-to-noise ratio events in these next generation detectors. And they're the ones that live down here, where now they're let's say easily detected. But in a third generation detector, they're right in the sweet spot, but way, way, way closer than the horizon. Right, so those have huge signal-to-noise ratios. And the rate, if you're willing to go a bit farther out, so to redshift of a few, and you can think of that donut I showed, that's where most of the population will live, is here somewhere, and still you have a really high signal-to-noise ratio on those. And that means you can start looking for the oddballs. You'll have some thousands of events per day. You shouldn't worry too much about confusion, because if they only last for a second, there are plenty of seconds in a day to do that. But you have some thousands of events in the universe per day, one every 15 minutes. And you can then pick the most interesting ones. Something that has a very high eccentricity, something with high spins, something with a large kick. You just pick the fun ones, the ones that explore the corners of parameter space. So that's the promise of this sort of variety that you get when you're detecting with high signal-to-noise ratio the events at a Z of a few. Right? So you just get tons of them. And the same thing for the binary neutron stars. There you're looking at as many as 1 million per year. And you do have to worry about the confusion of too many sources down here as you get many, many binary neutron star signals coming in. So that's an exciting, sort of the second exciting piece of the wedge. The third piece of the science wheel there was this blue wedge, which is about nuclear physics. And not really my area of expertise, but people who know this better than I do will draw a density temperature plot and say, these are the things that we can do with colliders, right? But this is exploring some other region of parameter space. So during the approach to coalescence, we call it in spiral. So as our two neutron stars are going around each other and radiating gravitational waves, you're down here, where you have something which is essentially zero temperature, nuclear matter, very dense. And you can look at the tidal deformations, and those are imprinted on the gravitational wave signal, and that lets you explore the equation of state of the neutron stars as they approach coalescence. And then once they merge and kind of go squish and make a great ball of neutrons in a big explosion, you're exploring this piece of parameter space as you're forming the nuclei in the R process. So it's a region of perimeter space which apparently is very difficult to explore on Earth with colliders of various sorts. So that's the nuclear physics side of this. You might have noticed that each of these, I put some little thing sideways over here about what DOE stuff we overlap with. A lot of these have, so historically we're all NSF. But there's a lot of overlap in terms of our science with the DOE stuff. So I put these little markers on the side saying what parts of DOE sort of mission do we overlap with. And we've recently participated in the whole snowmass thing, and that actually went quite well, and I think a lot of people are excited about gravitational wave detectors, so I wanted to put that on there as well. So I'm running out of time, and I might be running out of slides as well. This last piece is just sort of a nice piece of astro, and something which ends up driving a lot of our thinking about how to build these detectors. And it comes from localizations. I'll show this for the current generation of detectors. Here's the Hanford detector, here's the Livingston detector, and this is the Virgo detector in Italy. And let's see if I can make that animation go again. So I have some source that goes bang, and a signal comes out and arrives here first, and it arrives there second. And the relative timing, the arrival time of those two things actually gives you a location on the sky as to where this source came from, just from the gravitational waves. And our locations on the sky, if we have two detectors, people say they look like giant bananas. It's some big thing across the sky. And the reason why it's not a ring that you get from just pure timing is because we also have the antenna pattern information of the detectors, so we know that it's most likely coming from a place where we're more sensitive. And the two LIGO detectors are not quite perfectly aligned, so you get a little bit of which side information as well. But there are these, say, gigantic error boxes that are produced with two detectors. If you want to do good localization, you should have 3 detectors out there. So you might have seen this one arrives first here, and then over here, and then over there. And here I've thrown Virgo in the mix to get that third leg. And with this, you get localizations which, for us, pretty good. From an astro point of view, it's still square degrees, not arc minutes or anything that would be considered respectable from a point of view of a telescope, but much better localizations than you get with just 2 detectors if you have a network around the globe of detectors. This was our first binary neutron star event, and fortunately Virgo was on for that, and so we got a pretty small error box on that one. As we go to next generation detectors, the signal to noise ratio can be large enough that you can identify a source location before it merges. So this plot is showing the time to coalescence and the cumulative signal to noise ratio. And I will focus on these two, so ET and CE, and you can see that we could hit a cumulative signal to noise ratio of plenty for localizations, probably here somewhere, with some thousands of seconds pre-merger. Of course, this depends on what you choose for your source location. But as an example, this is 3 times farther away than the first binary neutron star. So the objective would be to point at some spot in the sky before the thing goes bang, so that people with telescopes can point there, or at least start slowing or do whatever people with telescopes do, to be ready for the thing to go off. Right? And there, once again, I'll point you to some respectable studies of how this works, which give numbers that are fairly optimistic. Several per year would have an early warning time of 5 minutes, where we could hope to have decent localization, 10 square degrees, decent for us, 1 square degree for a few, to really localize sources before they merge to point telescopes. All right, I will skip. I'm going to zoom out a little bit and talk about the context in which this will be happening. So the timeline for us would be It's probably on the next slide. Operating sort of, hoping to start operation mid-2030s. And that lines up with the European Einstein telescope, same sort of timeline for operation, and with the LISA space mission. So the LISA mission explores a different band, so it's not obvious that they have to be happening at the same time, but sources can actually evolve from the LISA band into the ground-based band. So you could potentially detect something with this space detector as it was leaving the LISA band at some millihertz, and say that's going to appear in the LIGO band or the Cosmic Explorer band if it's operational 3 years from now at 5:69 a.m. or whatever. I mean, you can tell exactly what it's going to be, and that's something you predict from the signal you get at low frequency and the evolution of the source. So that's the sort of gravitational wave network that we would be operating in at the time, along with the existing detectors for as long as they can be made to operate. So we'll have the existing network going. We call it the 2G network operational, along with these next generation detectors. The very rough timeline for us, and I'll focus on just a couple of these blocks, is that we've finished up our Horizon study, and we're moving now into the design stage for Cosmic Explorer. And this we expect to last, I mean, I'll be frank, everything on here is optimistic, and I think we will acknowledge that. If you gave me all the money I asked for, this would be the timeline. Anyhow, so something like 7 to 10 years worth of design, and then we start construction, something like 5 years of construction, and then we start commissioning and observation. So mid-2030s is sort of earliest possible, I think, date for a Cosmic Explorer operation. There's a lot of stuff that has to go on at the same time. One piece is this site search. So everyone always asks me, so where are you going to build this? And the answer is we don't know yet. I used to put up maps with little L's on them, and then I realized that people get nervous if you draw a little L on their home. So I stopped doing that. So we don't know where we're going to build it yet. And there's a lot of work that goes into finding a place. And I'll say a word about that in a second. The process by which this happens is, for us, for now, we're following NSF in terms of the process. So this is known as the MREFC process. If you want to figure out what that is, it's uncompressed there. And the NSF has become reasonably prescriptive about this over the years. So it means that at least if you don't know what you're doing, you can read the book and follow the timeline. This 3 to 5 years I've asked is actually wrong, but that's what it says in the book. But we're just entering this conceptual design phase right now, and we'll be progressing along this over the next several years, looking for Congress to decide that we should be funded somewhere around here, and then a couple more years for that to actually happen, and then construction beginning there. Okay, we took it as a good sign that the recently published Research Infrastructure Guide, which lays out all the plans, put a gravitational wave event on the cover. Like, you can't beat that, right? It means that someone on the inside is rooting for you. Okay, so the Cosmic Explorer project is now many institutions and quite a range of folks. I don't expect you to read any of this. Working on it, but right now it's a mostly volunteer effort. So these are everyone who can afford to spend some time helping us out is doing so. We just recently submitted a whole collection of proposals to the NSF. So this is 7 coordinated proposals just went in to work on various aspects of Cosmic Explorer, focusing on sort of the longest pole in the tent is the site selection part, but trying to get progress made on sort of all of the detector subsystems and the vacuum system and all the other stuff that needs to come together. So that's the state of affairs right now for Cosmic Explorer. And before we wrap up, I want to return to the very beginning of this talk where I didn't do a land acknowledgement and say a few words about that. So this graphic, which was made by a Cal State Fullerton undergrad, Eddie, who heroically drew all of this despite being unfunded by, so anyway, we're going to have to pay architects a lot of money to make something better, I guess is the way I want to say this. And we're going to do that. But anyway, I'm always impressed at what our undergraduates can do. So anyhow, so this is our view of the site, and we have this vast open plain out here that we're building on, and the image is appealing, I think, to people like me who think about the instrument and the science and all that, and don't like to worry about the social aspects of the work that we do, because there's nothing social about that, right? There's nobody there, right? That's the idea. Find some big place in Arizona or New Mexico or whatever. There's just nobody there, and build whatever you want. And I've come to realize through the help of a number of folks that there aren't places like that around the US. And someone at some point sent me to this map. Said, go look at this map, nativelands.ca, and tell me where you're going to build something that isn't the home of somebody, right? And you look at that and you say, well, maybe there's a little wedge over there, I don't know. But there's no place, actually, it turns out, in the US where you can go build something and not be stepping onto somebody's home, right? So that's why I stopped showing maps with little L's drawn on them. Because if you do that, then you're basically saying, hey, I'm going to go build in your home, but I haven't asked you about it. So right now, one of the things that we're thinking about a lot, we're spending a lot of time thinking about how do we approach the process of building a large facility in the US in a way that respects the ancestral ties that indigenous people have to the land that we're going to build on, and actually doesn't approach this as this is some gigantic problem, I wish I could dodge it, but rather as this is a huge opportunity to do something good. I'm going to have $1 billion to work with. Maybe I can actually do something really awesome here and improve the relationship of science and indigenous peoples, which has been in rather bad shape. I'm thinking of TMT in particular of late. We've not been doing great here. So can we put a model for doing this better? So this brings me back to the land acknowledgement. It's not the one at Stanford, but the one that I put up for Cosmic Explorer team, which is just to start by saying that we recognize that this is the place we're looking to build, and it's not a place which is empty, right? Despite the fact that scientists like me, I'm not going to point any fingers, like I'm the first guy who likes the big empty plane idea when I'm thinking about it, because it's uncomplicated, right? But it also misses a huge opportunity. So we're taking this very seriously and trying to figure out how we can be a model that other projects would like to follow. My mother used to say, if you try to do something in life, you will either be a great example that people can follow or a horrible example that people can learn from, right? Either way, you've done something good, right? So we don't want to be the horrible example that people can learn from, like what they should not do. There are plenty of those out there already, actually. So this is where I want to sort of wrap this up, saying right now for us, we like to look at topographic, the topology or topography rather of sites and think about how much land or earth moving we need to do to build a site. It turns out that if you just go to someone who lives there and say, we're going to come to your place and do a lot of earth moving, right? You're already in deep trouble, right? You're already in deep, deep trouble. Just the choice of language is important. And you can understand why, right? People have been showing up and doing earth moving on their home for a long time. So this is a big thing for us, and we're trying to figure out how to do it right. Let me very briefly, to emphasize that point, go back to this slide and say, this is the Community and Land Partnerships Office, right? This is our Director of Community and Land Partnerships, right? She is someone I talk to very regularly, right? She worked on the astrodecadal and thought about exactly these sort of societal implications. So we have some really good people who are volunteering their time to help us get this right, because it's a tough thing. All right, with that, I will wrap it up and say that Cosmic Explorer is, for right now, it's a vision. I think that hopefully by summer, it'll be a vision with a few $1 million in the bank. We had a few $1 million a while ago when we spent it. We wrote the Horizon study. I think that was a success. But this is our concept for where we're going. It has a fair amount of, I didn't show the quotes from the astrodecadal or from SNOMAS, that there's I think a pretty good consensus is the right way to go in the community, our community, but also more broadly. So we're really excited about this. A lot of people are very excited about it. There's a lot of great science to do. There's some very complicated issues to address when it comes to building large facilities. They're mostly not technical issues. Okay, I'll leave it there. Thank you.
All right, thank you, Matt, for the nice talk. Bob, will you be narrow banding around 100 hertz to look for coherent sources?
Narrow banding around 100 hertz? Absolutely not. Why would we do that?
LIGO's has done it.
Narrow banding?
Yes.
What? We never narrow band. We never know. So the original LIGO design had narrow banding, which was a detuned interferometer. If that's what you mean, that's what we usually call narrow banding. Is that what you're thinking of? We never actually did that. It turns out that detuning the interferometer for detuned narrowband operation is not a good idea. And it's not a good idea because you need to redo your entire control system in order to operate in a weird regime in which, I'm going to use some technical jargon and hope that this flies, all of your sidebands become imbalanced when you move away from resonance, and your whole control system becomes first messy because you get all kinds of offsets, but also it's a completely different control system. So you need to rebuild all of your electronics. It's a huge effort that required to narrowband. In the end, we never did it. And it turns out that if you actually put in realistic losses for the interferometer, there's not even a big win. So narrowbanding was something in the original idea for LIGO, something that we would do. It's actually not a win. Part of the reason for that is not something that was anticipated originally, which was squeezing. So right now we can gain by using squeeze light, and it turns out that squeezing and narrowband are more or less exclusive. So you wouldn't bother narrowbanding because you have a broadband way to lower the noise through squeezing. So we haven't done it, and we won't. Yeah.
Peter was next.
You mentioned the comparison between the Einstein telescope and
See? Yeah.
Cosmic Explorer.
That thing I've been talking about.
That Einstein, they were planning on part of it being cryogenic. And I'm just wondering, what's the trade space there? I notice you're not considered cryogenic. And the second question is, what's Japan doing? Because they are doing that.
Yeah.
Maybe you could update us on that.
Yeah, so let me get back to the sensitivity curves. Okay, so the Einstein telescope is a triangular underground detector. And as a triangular detector, you lose because of the angle, not a lot, but you lose something. But you can then put 3 interferometers in your triangular tunnel system. That's already sounds like a bit of a nightmare from someone who's built interferometers, because just getting one to work is tricky. Getting 3 of them to work simultaneously is really, really tricky. But that wasn't enough. So this sensitivity curve has this sort of funky shape to it, because this piece comes from the low frequency detector, and that's combined with the high frequency detector, which looks like a kind of LIGO-like sensitivity curve. Right? And this is a detuned narrowband operation around these low frequencies, which then has a crazy control system, blah, blah, blah. It also is very hard to use squeezing with because you need multiple filter cavities. So anyway, that's the low frequency detector, which is cryogenic. And the high frequency thing over here is room temperature. Okay, so to me, and I think to many instrument builders, the design which produces this curve looks really, really tough to actually achieve. And that means that each leg of the triangle is 2 interferometers. So you actually have 6 detectors operating simultaneously. 3 of them are cryogenic, and 3 of them are room temperature. The 3 cryogenic ones are detuned, low frequency, blah, 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 really, really hard to operate detectors. So I think this is really hard to achieve, is what it comes down to. And I didn't want to suggest a detector that I didn't think we could build. So Cosmic Explorer is basically saying, let's take technology that we know. Let's imagine incremental improvements, which will get us some better low frequency performance. Some of this is coming from length, some of this is a little bit higher power. So relatively modest improvements to get to this curve. But instead of doing, Cosmic Explorer is 40 kilometers for that curve. ET is 10 kilometers, but 60 degrees, so it's more like 7 kilometers. So this is a lot of technology improvement and a factor of 2 improvement in length, right? Whereas Cosmic Explorer is make it a lot bigger and improve the technology in a modest way. It's a rather different approach. You asked about COGRA. COGRA is exploring cryogenics. They're having a tough time of it, and their sensitivity will be somewhere up here. They built a 3-kilometer detector underground. It's never going to be bigger than 3 kilometers, so they will stay up here forever.
But where's the underground feature of Einstein? Can you? So what? Why? Oh, that's the very low frequency.
This piece. So if you want to go, so we're limited here. We sort of say, let's make the suspensions and the isolation systems and everything as good as it can be. You end up sitting on Newtonian noise, the gravitational background. We call it Newtonian noise, but it's really gravitational fluctuations due to seismic waves or atmospheric disturbances or whatever. That ends up being the thing which you're sort of sitting on at the low end. And the way you can escape that is to go underground. You escape the atmospheric part, you escape the surface seismic waves, and you're bathed in the body seismic waves. So the ET folks plan on building underground to carve out this little wedge over here, which on this plot looks totally insignificant, and I don't know why anyone would go to that much trouble to do it. If you go to the next plot, they will say, this is why we do that. And it's because for the really heavy sources, it puts you at a bit higher, SNR, factor of several higher SNR on the heaviest sources. Right, so this is the science that you carve out with that little extra wedge in frequency space. The other reality is that a huge surface detector in Europe is really, really hard to find a place for. So in the US or Australia, it's not so crazy. But in Europe, it's really tough.
Other questions? Yes.
What is the current limitation on the understanding of the tidal deformations in binary neutron stars? Is it like theoretical? Is it not like theories up there yet? Is it that LIGO is not sensitive to those fluctuations the way it formed yet?
Yeah, so we were able to put some constraints. So the way that I usually see this talked about is you say, here's a collection of equations of state which come from some models of what's going on inside the neutron star. And you give them all 3-letter acronyms. You make a plot with a bunch of mass-radius relationships. And that's the usual way I see that presented. And each of the curves on that mass-radius plot is coming from some equation of state and some model. And we were able to chop off some chunk of those and saying it's not, not the really squishy ones, something like this, right? But people will say we chopped off the crazy ones. There are plenty of available theories that we can't distinguish right now. So I think that that was basically one event, 1708-17. So as we get more by neutron star events, and certainly as you go to next generation detectors, then you could have really high signal to noise ratio on that in spiral part, which would allow you to constrain tightly the equation of state. Right now, we're just we've eliminated some of the crazier equations of state for binary neutron stars.
Roger.
Could you go back to your sensitivity curve? LIGO India would be what is its aspiration relative to the great curve there? And if it happens, what will it give you in terms of the physics reach?
That's a really tough crowd today. LIGO India is planned to be a 4-kilometer instrument, right? So I would say the same rules apply. The idea is that when LIGO India is built, it will be built to match the existing detectors. So if the existing detectors are at one of these 2 curves, I don't know when in the future LIGO India will be built, but let's say it was built at the same time as our second round of upgrades for A+.
Having that ambition.
Yeah, so it is intended to match the LIGO detectors.
Oh, well,
right?
Yeah, okay, with that technology, great.
Yeah, right. So I mean that I could stop there, but I mean the obvious downside, if you look at the timeline, is that this business is all go back. You know, here we are here, and this is when we're at the A+ curve, right? And that's not far from the best you can do, and not far from Cosmic Explorer and ET coming online. They haven't started construction yet, so when is that detector going to be useful? I don't know. That's construction, so you finished building here, now what do you do? Right, so I don't really know what's going to happen with LIGO India. It's been delayed so much that I start to wonder if a 4-kilometer instrument really makes any sense.
How does the cost of the Einstein telescope compare to Cosmic Explorer? I mean, one is larger, the other one is underground and has higher, allegedly fancier technology.
Yeah, so I think ET is significantly more expensive, but they're the same order of magnitude. The truth is it's really hard to compare because European costing doesn't put salaries in, and all of our expense is salaries. So they say, all right, now how do I compare those two numbers? Right? It's tough. But well-known problem. So the numbers that come out of ET are similar to our numbers. Right? So they say this is going to cost $2 billion, or 2 billion euros, and we're going to cost $2 billion, right? To build 2 observatories, 2 CE observatories in the US, $2 billion. To build ET, which is a single underground triangle with 6 detectors and blah, 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 2 billion euros. And you say, all right, so they cost the same. You're like, wait a minute. You guys didn't include any of your personnel costs in there. Now what? Well, I don't know. I don't know how to get that number.
Yeah.
So within a factor of 2, maybe they're the same. I don't know.
Last question.
Okay, it's more of a comment, that's why I waited for last, which is I find it very interesting to think about a future where you have 1,000 events per day, and that's just in one category of type of physics. Do you think it's conceivable you could audio stream the data out to the public so that they could listen to this like a podcast? And it seems to fall within NSF's themes of broad outreach and reaching the public and stuff. I'm hoping that idea makes it out to
I think this has already been done for LIGO. It's just a really boring channel.
Okay, yeah, so the event rates, if they're really high, I think maybe
Yeah. But I think it's already done. Like there is already some app that you can get which you can play events on or something like that. When they happen, it like goes beep and then plays the event for you or something. But you could have a live stream. Yeah, sure, why not? I guess everyone would think that was really cool for the first 10 minutes and then turn it off. But
okay, and on this note, thanks a lot.
Sure.
So actually, polarization. You haven't. So have you guys started